Hello, so today I want to share with you our solution of leveraging the cloud ability to travel through time and space to schedule our high-performance computing workloads to regions where data centers are powered by renewable energy, thus reducing our carbon footprint. I'm Lisette van Leeuwen. I work at Ortec Finance as a software engineer. I'm a proud aunt of 2, and I am a passionate reader and yoga practitioner. You can contact me in person or via my contact details listed here. Before we dive into the mechanics of high-performance computing, let me tell you something about Ortec Finance. In a nutshell, we build and design advanced analytical models, wrap them in software, and ship them as SaaS solutions to our clients, which range from pension funds to insurance companies and sovereign wealth funds. With these solutions, clients can manage their investment decisions. We have a global client base and 2 self-managed data centers. So by design, we are unable to keep up with the growing demand of hosting in other jurisdictions. And this is part of the reason why we decided to move to the cloud. And with moving to the cloud, we also need to move our high-performance computing workloads to the cloud. Today, I will tell you something about how we did that. So right now, we have a high-performance computing design on bare metal in our own self-managed data centers. Obviously, we need to move away from that, so we looked at our requirements for our design in the cloud. At first, it needs to perform at least at par with our current bare metal solution. It needs to scale up, obviously, but it also needs to scale down to save on costs. And with our very large client base, we also need to be able to perform multiple tenants at ease. Now, we are not married to one hyperscaler or Kubernetes distribution. And also, upcoming European regulation requires vendor exit strategies, which makes vendor independence more important. Unfortunately, none of the managed solutions fit our design. So we decided to design it ourselves. We chose for managed operators as well as do-it-yourself components. And for the managed ones, we chose Red Hat operators to ensure Red Hat support. We chose to use Prometheus, the custom metrics autoscaler, Knative, as well as ActiveMQ. So we assembled all these parts together in this architecture, and we will run through it together. So our user wants to start a simulation and sends a request to our gateway API. It starts up and sends a message to a job queue. The Prometheus alerts the CADA operator to scale up the managers. And the manager is just one of our do-it-yourself projects. It manages a direct acyclic graph, which means that tasks can result in new tasks. Tasks are sent to the task queue. And Prometheus again alerts the CADA operator to scale up the workers, which are again our own applications. Workers execute a task and send the results back. Scaling up is easy. We just add more machine sets. And with tolerations and taints, we control the chipset, memory requirements, and GPU availability. Everything scales down to 0, which saves on costs. And the queues are there for resilience. So if a pod gets scaled, it doesn't impact the simulation. Now let's also look at carbon emissions, because that's what I'm talking to you about. So the International Energy Agency estimated that the global electricity consumption of data centers was 460 terawatt hours in 2022. And this will increase to more than 1,000 terawatt hours in 2026, which is the equivalent of the electricity consumption of Japan. Now, in response to these high numbers, governments worldwide introduced a set of rules and regulations to reduce the energy consumption, promote renewable energy, and decrease the carbon footprints of data centers. The CSRD even requires companies to report on their carbon emissions, which makes this even more important. But how do we quantify those carbon emissions? Well, if you want to know how much energy your computer consumes, you can add a device to your socket. But what if you share that computer with your family? How would you determine the electricity consumption attributed to each family member? Given virtualization and containerization in the cloud, this is even harder. The solution here is Kepler. For carbon intensity, it's even harder. But we do know the carbon intensity of electricity used by our data centers. For this, we would need live and predicted data, which can be retrieved with a grid intensity provider, such as electricity maps or watt time. Given these two together, gives an estimation of the carbon emission of our simulation. Now let's see how we use these things together to make our high-performance computing design a little bit more green. Here I show you the architecture that we designed. So we created an operator on top of the high-performance architecture that I showed you before. Now you see here two clusters, one in Europe, one in North America. Let's dive in a little bit. So our user sends a request to our gateway API again. This time, the message is sent to a dispatch queue. And the Prometheus again alerts the CADA operator to upscale the dispatcher. The dispatcher looks at the grid intensity provider to determine the grid intensity for both clusters. If the grid intensity is lowest in the European cluster, it will send a message to the job queue in that cluster, and then the manager and workers are scaled up. If the North American cluster is a little bit more green, it will send a message to the bridge queue, from where it will be forwarded to the job queue in the North American cluster, and the simulation is executed in North America. On the North American side, we also have the exact same setup, so we can do this both ways. Now let's see how this looks like in action. All right, so here you see a map of the grid intensity for each region. Now if we zoom in to the Netherlands and California, let's assume it's daytime in the Netherlands. So we have a lot of solar power, which is quite green, so low grid intensity. On the other side of the world, it is now nighttime, so larger grid intensity. Our dispatcher uses these numbers. So now we see here two clusters, one in North America, one in Europe. My colleague in the Netherlands, let's imagine that he sends a message. He wants to start a simulation. He sends a message to our gateway API. You just saw it pop up. It then sends a message to the dispatch queue, and the dispatcher comes up, as you see there. The dispatcher looks at the grid intensity that was just shown on the map, decides that grid intensity in Europe is lower, so it will send a message to the job queue, and the simulation is started there, as you can see here now. Now, if we look at the numbers in the bottom, we see the CPU utilization and the energy consumption. These numbers are retrieved using Kepler. It also shows the grid intensity that we just saw. And given the energy consumption and the grid intensity together, gives an average estimation of the current carbon emissions of this simulation. Now, as this simulation is progressing, and I think it's going to finish soon, let me tell you something about this project. At Ortec Finance, we call our OpenShift cluster the Ortec Finance Container Application Platform, which is quite a mouthful. That's why we abbreviate it to ORCA. And to stay in line with our ocean theme, we decided to call this high-performance computing design Sailfish. Now, why do we call it Sailfish? Because it's the fastest fish in the ocean. So now we see that the simulation is shutting down. The last worker is still there. I think it's the manager, by the way. It will shut down soon enough. And then we will continue to a second simulation. Now let's look at the map again. Let's assume nighttime has fallen over the Netherlands, so grid intensity is very high. On the other side, it's sunny California, so grid intensity is very low. This time, my colleague, he has a deadline. He needs to work at night. Poor him. He sends a message to our gateway API again, which is then sent to a message to the dispatch queue. The dispatcher pops up in the Netherlands, looks at the grid intensity provider, and decides to move it to the North American cluster, as you see here. Now I hear you asking, can we use this for other purposes? Yes, you can. This operator that we designed uses just the metrics to schedule the workloads based on carbon awareness. But you can also use a metric for GPU availability or costs. For example, in Scandinavia, data centers are powered by hydropower, which is quite green, but data centers are also very scarce there. So availability might be an interesting metric to use there. On the other side, in West Europe, due to popularity, costs are increasing. So cost might be an interesting factor there as well. So this operator that we designed is widely applicable. So now that I told you the story about sailfish, you also recognize the logo, right? It's a green sailfish. So if you want to know more about our project, you can look up at our public repository on GitHub, where we also have a lot more videos, including the one I just showed you. Again, here are my contact details, so please feel free to contact me. Thank you.